Okay, so here we have started recording. So this is our simple aircraft cooling system. In this, you can see that this is the tunnel in which compressor and gas turbine is fitted. This is your compressor. This is your compressor, gas turbine, combustion chamber. The air is, as airplane is moving in this direction, so air is moving in opposite direction. Because of kinetic energy of the air, whatever the natural compression will happen, that is called as ramming of air. Okay, so after ramming, yes, so some air we are bleeding off. Yes, so whatever the compressed air is there, some air we are taking off for the refrigeration purpose, right? So this is your heat exchanger. This is the heat exchanger, right? So this ram here, this rammed air, now this compressed air we are bleeding off, and this air we are sending into the heat exchanger. You can see here. Okay, this air we are sending it to the heat exchanger. Now in this heat exchanger, the air is cooled by the ram air. Though rammed air is a compressor, its temperature is comparatively lower than that of the compressed air. So that rammed air could be used as a coolant in the heat exchanger, right? So this is your heat exchanger. It is very simple. So this, after heat exchanger, it will be sent to where it will send. Now here we can use to exit this. What we can use here, this with the help of cooling turbine. This is your cooling turbine. Okay, on this cooling turbine, this fan is mounted so that rammed air will come out. Right? So this is your cooling turbine, and after that, your cold air to cabin. Very simple. I hope all of you understood. In 1 minute, I will repeat it. Please understand. This is your aeroplane which is moving in this direction. So air will move in opposite direction. It is a compressor and gas turbine. They are coupled. Okay. So air will get compressed. Then it will go to the combustion chamber. Combustion will take place. The hot gases will expand into the gas turbine. It will produce the work, and it will create the thrust. And your aeroplane is moving. That's not our part. Our part is what? Refrigeration, cooling, right? Now some air from the compressed air, some air we are bleeding off. Some part of that air we are taking and we are sending it to the heat exchanger for cooling. And for cooling of the air, we are using the rammed air, whose temperature is comparatively lower than that of the compressed air, right? Then after cooling, this air we are sending it to the cooling turbine. In cooling turbine, the air will get expanded. After expansion, pressure and temperature will decrease. So that low pressure, low temperature, cold air, we are sending it to the cabin, into the aircraft, right? That is how the simple aircraft cooling system or simple air cooling system works in case of aeroplane, right? Now there are different processes. So this process, try to understand on the TS diagram. Let us try to draw the TS diagram. Temperature versus entropy. Now TS diagram indicates heat addition or heat rejection. Area under TS diagram indicates heat addition or heat rejection, and area under PV diagram indicates work Done. Right? Okay. Now, what are the processes? First, ramming, then next compression, then cooling, and then expansion. Right? So these simple processes are there. Okay. And then after cooling, after expansion in the turbine, it goes to the cabin, and where it is absorbing the heat from cabin. So refrigeration inside the cabin. So total how many processes? 5, right? Ramming, compression, cooling, expansion, and refrigeration inside the cabin. Heat absorption, right? Now let us try to draw. On TS diagram, there are constant pressure lines. Okay? So these are the constant pressure lines. So this constant pressure line is of atmospheric pressure. The cabin pressure is little more than that of atmospheric pressure. Then ideal ramming, actual ramming. This line is of compressor pressure. So all these lines I have drawn. These lines are constant pressure lines. So this is what? Air pressure. This is what? Cabin pressure. This is what? Ideal ramming pressure. Ideal ramming pressure, and this is actual pressure. Right? This is what? Compressor pressure. Okay? So the first, atmospheric air pressure or atmospheric air pressure. So from atmosphere, what will happen? This. So first process is what? 1 to 2. 1 to 2 is what? Ideal ramming. Right? But ramming will not happen ideal. So actual ramming pressure will be less than that of the ideal ramming because of friction. Right? So, but temperature will remain same. That is your 2 dash. Right? So the process 1 to 2 dash is what? Actual ramming process. Okay? Next process 2 to 3 dash. 2 to 3, 2 dash to 3 is what? Isentropic compression inside the compressor. Because of the irreversibility friction, the actual compression, the temperature will increase than that of ideal case. Right? So actual case will be like this. 2 dash to 3 dash. 2 dash to 3 dash is what? Actual compression. Right? Then 3 dash to 4 is what? Here. This is the condition 1. Ramming is the condition 2. After compression condition 3. 3 to 4 is what? Cooling of the compressed air inside the heat exchanger. Right? So 3 to 4 is what? Cooling process. Okay? Then next 4 to 5 is what? 4 to 5 is what? Isentropic expansion inside the cooling turbine where pressure and temperature is reduced. But actual case will not be isentropic. Isentropic means what? Reversible adiabatic, which is not possible. So, whatever the temperature drop that we expect, that drop will not achieve. So, in actual case will be like this. 4 to 5 dash. Right? And 5 dash to 6 is what? 5 dash to 6 is what? Cooling or heat absorption inside the aircraft cabin. Right? So this is your TS diagram. Okay. Now let us. All of you understood this, right? Now let us try to understand each process and formula involved in each process, right? This point is very important. If you understood this, you can understand all the aircraft cooling systems. There are 4 aircraft cooling systems: bootstrap, reduced ambient, and regenerate. Right? So the formulas are same, only the arrangement is different. So please try to understand formula here only. Okay. So first process is what? Ramming, which is 1 to 2, right? Ramming process. Now why the ramming is, as I have said, because of kinetic energy of the air. Because of high velocity, it possesses very high kinetic energy. If anything hollow moving fast inside the air, so that kinetic energy of air will get compressed. So that natural compression because of high velocity is called as ramming, right? So that ramming will happen. So this ramming is in the form of kinetic energy, which is equal to, what is the kinetic energy? 1 by 2 mv square. But here we are taking per unit mass. So we can take directly v square, joule per kg. Right? In book, they have taken kilojoule per kg, so divided by 1000 they have done. Right? So kinetic energy here, what is the change in kinetic energy here? Change in kinetic energy is what? Change in enthalpy, which is H2 minus, H1, right? H2 minus H1, which is 1 by 2 V square, right? So we know what is enthalpy. Enthalpy is nothing but Cp into temperature. So Cp T2 minus T1, which is equal to 1 by 2 V square. T2 is what? Temperature after ramming, and T1 is what? Atmospheric temperature. So we are interested in calculating the temperature formula after ramming. In ramming process, what is our target here? To calculate the temperature of air. What change happens in the temperature of air because of ramming? Right? Ramming happens because of kinetic energy. That's how we have taken the kinetic energy. Right? So because of that, air stagnation will happen. Little air stagnation will happen. So here take the Cp common, which is T2 minus T1, which is equal to 1 by 2 V square. So T2 minus T1, which is equal to 1 by 2 V square by Cp. So take T1 on this side. So T2 is equal to T1 plus 1 by 2 V square by Cp. So divided by T1, so T2 by T1, which is equal to T2 dash by T1. Here, you can see here, T2 is equal to T2 dash. Pressure is different, but here we are considering temperature is same. Right? So T2 is equal to T1, which is equal to T2 dash by T1, which is equal to 1 plus 1 by 2 T1 Cp into V square. Right? Clear up to this? Yes or no? Up to this it is clear? Okay? Don't write, you just try to understand this. Now, instead of Cp, I would like to put that Cp in terms of gamma and R. We know that Cp minus Cv is equal to R. Do you know this? Right? So, take the Cp common. Cp is equal to 1 minus Cv by Cp, which is equal to R. Right? Now, what is Cv by Cp? We know gamma. What is that? adiabatic index, which is equal to Cp by Cp. So Cp by Cp is nothing but 1 by gamma, correct. So Cp is equal to 1 minus 1 by gamma is equal to R. So Cp, give this as equation 1. So Cp is equal to gamma into R divided by gamma minus 1. Right? So put this value in equation 1. Put this in equation 1. Okay? So T2 dash by T1, which is equal to 1 plus gamma minus 1 into V square divided by gamma R into T1. Right? Now we know that a local velocity, that acoustic velocity of the sound. Acoustic velocity means what? Sonic velocity. The speed of sound inside the air. Can we calculate the speed of sound inside the air? Yes, we can. By using which formula? Let us consider A is equal to sonic or acoustic velocity in the air of sound की velocity, right? So which is equal to under root gamma R T1. T1 is the temperature, local velocity, local temperature of the air, right? So here we have gamma RT. So under root of gamma RT is equal to A, so that we can write gamma RT is equal to A square, right? So T2 by T1, which is equal to T2 dash by T1, which is equal to gamma minus 1 into V square by A square, right? So here this is the formula to calculate the temperature, right? If suppose we want to calculate, now what is velocity of object divided by velocity of sound? What is that? You learn this in the fluid mechanics. Velocity of object divided by velocity of sound is nothing but Mach number, right? So here we can write m square into gamma minus 1, right? Divided by 2. Don't forget this, divided by 2. Divided by 2, right? Okay? So from this you can calculate temperature of the ramming after ramming process. Temperature at the end of ramming, right? We also know that T2 by T1, which is equal to T2 by P1 raised to gamma divided by gamma minus 1. What is that? This is the pressure temperature relationship for the isentropic processes. Or this relationship you can also like this: T2 by P1, which is equal to T2 by T1 raised to gamma minus 1 by gamma, right? What is m here? Velocity of object divided by velocity of sound in air or in that medium. That is nothing but your, right? If Mach number is equal to 1, we are saying that aeroplane is moving at a velocity of sound. We call that sonic velocity or sonic aeroplane. If the Mach number is less than 1, then that is nothing but sonic velocity. If Mach number is less than 1, it is called as subsonic. If Mach number is more than 1, it is called as supersonic. Most of our fighter planes are moving at a supersonic speed, right? So that is your supersonic. And what is hypersonic? If Mach number is more than I, then it is called as hypersonic. Or sometimes Mach number is greater than 3, right? Our missiles are hypersonic. BrahMos missile is hypersonic, which is moving at a Mach number of more than 3. Somewhere it is considered 3, somewhere it is 5. So it is hypersonic. Means velocity of that object is much more than that of the speed of the sound. How much time it takes to reach my sound towards you? Just in no time, right? So imagine the velocity of missiles and aeroplanes. Okay? So this is your ramming process, right? So we can also calculate the ramming efficiency. How to calculate ramming efficiency? Actual change in pressure. Actual change in pressure divided by ideal change in pressure. Okay? Now, next process is what? After ramming, compression, which is equal to 2 dash to 3 dash, actual compression, right? So what is the formula for compression? 2 dash to 3, you can consider here 3. Okay, so the work required for the compression process inside the compressor happens isentropic compression. So what is the work of compressor required? Formula is what? Look at the TS diagram. Compression 2 dash to 3 or 3 dash. In case of isentropic, 2 dash to 3. How to calculate? Hello, second class students, please settle down to discuss. How to calculate work of compressor? You know how to calculate? How to calculate work of compressor? mCp delta T, right? Mass of the air flowing Cp into T3 minus T2 dash, right? Power required for the compressor, which is equal to MACP into T3 minus T2 dash divided by 60. If you want to calculate power in kilowatts, right? Then next process is what? Cooling. A rammed air is used for the cooling of compressed air, so that high pressure compressed air temperature will be reduced 3 dash to 4 in the TS diagram, from 3 dash to 4, right? So this cooling in heat exchanger. Okay, so what happens cooling in? So heat removed from the MACP into T4 minus T3 dash. Cooling in the heat exchanger. Next is what? After cooling, expansion in cooling turbine. Expansion in cooling turbine, right? So because of expansion in cooling turbine, its pressure and temperature will reduced. So heat will be reduced, right? Okay, here this 4 to 5 is what? Actual expansion, sorry, isentropic expansion, and 4 to 5 dash is what? actual expansion, right? Here 0.5, T5 is here and T5 dash is slightly higher. Here also T3 is here and T3 dash is slightly higher, right? Then next process is what? Heat absorption inside the aircraft, right? Cooling process, which is 5 dash to 6. Heat absorption in cabin, or it is also called as refrigeration process, right? So heat absorb is equal to MACP into T6 minus T5 dash, which is T6 is what here? Temperature of the air entering inside the cabin, right? Sorry, here उल्टा होगा ये. T5 minus T5 dash minus T6. नहीं बराबर. T5 is higher ना? Sorry, T6 is higher. T5 dash is what? Temperature of the air which is entering inside the cabin here. T5 dash, which is temperature of the air entering inside the cabin, right? So cooling process is what? 5 dash to 6. Understood all these formulas? Okay. So here to calculate mass of the air, we can use 210Q divided by Cp into T6 minus T5 dash in kg per minute. When we are taking that factor 210, when here, if we want to calculate air in kg per minute, mostly they will ask to calculate air in kg per minute. Numericals will be asked on this. Is very important on listening, right? So all of you understood this simple air cooling system. Same formulas will be there for remaining 3 cases, right? Only the arrangement is different. So what we have seen here in this arrangement of this cooling system, TS diagram, different processes, ramming process, in that we have calculated ramming temperature, right? What is Mach number? Then compression, the formula for compression work. Then cooling, heat absorption in the cooling process. Okay, formula of compressor work, formula of ramming process, and formula of heat absorption inside the cabin. That is important. And the last point, COP. What is COP? Coefficient of performance, which is equal to refrigerating effect divided by working force. Refrigerating effect divided by work input. What is refrigerating effect? What is refrigerating effect here? Refrigeration process, heat absorption. What is that? MACP T6 minus T5 dash divided by work of compressor. How much it is? MACP into T3 minus T2. So COP is equal to what is T6 minus T5 dash divided by T3 minus T2. Right? Our target is to calculate. They may ask mass flow rate required. They may ask COP. They may ask work of compressor. If they will ask COP or mass of air required, then in that case, the compressor works needs to be calculated. Temperature and pressure at each stage needs to be calculated. Right? For that, temperature pressure relationship will increase. Understood all of you? Right?